10.3 Lesson 3, Parametric Equations and Calculus. Our objectives for today's lesson are understand the proof of Theorem 10.8, arc length in parametric form, and find the arc length of a curve given by a set of parametric equations by using Theorem 10.8. Vocabulary, arc length, and parameter. In section 7.4, we derived this definition of arc length, and you can refer to the lesson for that. And today we're going to start here and derive Theorem 10.8. The problem is the same, arc length. The difference is, in section 7.4, we had an arc that was described by a rectangular equation, and in section 10.3 we have an arc that is described by a set of parametric equations. So when we had our curve represented by a rectangular equation y is equal to a function of x on the interval of x values from x naught to x sub 1, this was the formula that we used. Let the function given by y is equal to f of x represent a smooth curve on the interval from a to b. The arc length of f between x is equal to a and x is equal to b is given by this integration formula. Now, in my diagram, I changed it from ab to x naught x sub 1. So I would change this just from AB to x naught x sub 1 to be consistent with the diagram that I have here. So today we're looking at a curve that is in the xy plane, but now our curve is described by a set of parametric equations. Y is equal to some function of the parameter t, and g is equal to some other function, or possibly the same, but most likely, in most cases, these are different functions. That's why we have f and g. So y is equal to some function of t, the parameter t. And we have a smooth curve given by a set of parametric equations such that the curve does not intersect itself on the interval of parameter values from a to b, except possibly at the endpoints. Then the arc length of the curve over the interval from t is equal to a to t is equal to b is given by this integration formula. And we're going to see how we get this from what we had in section 7.4. So why is it that the limits of integration change from x naught x sub 1 like we had in the previous section to a, b? We'll discuss that now, and then we'll look at the derivation. So when we look at our problem from section 7.4, the interval of x values was from x naught to x sub 1. We're saying that x is equal to f of t. So we're doing a substitution. We're saying let x be equal to f of t. And if you look at our diagram here, we have a point where the x-coordinate is f of a, and that would correspond to x naught from section 7.4. And the other endpoint of our curve is f of b, and that would correspond to x sub 1 from section 7.4. So that is why x naught is replaced with a, and x sub 1 is replaced with b, because those are the values of the parameter t that would give us the corresponding endpoints of the curve. So we will read through the derivation. Arc length. You have seen how parametric equations can be used to describe the path of a particle moving in the plane. You will now develop a formula for determining the distance traveled by the particle along its path. So if you're finding arc length in the context of motion in the plane, then you're finding the distance traveled by the object as it is moving along the xy plane. So we talked about section 7.4. There we learned the definition of arc length of a curve C given by a function h of x on the interval of x values from x naught to x sub 1. So this is the integration formula that we had for arc length in section 7.4. Now, of course, h prime of x is the derivative of the function with respect to x. So you can write that as dy dx. So that's how we go from the first line to the second line. If C is represented by a set of parametric equations on the interval from t is equal to a to t is equal to b, and dx dt, which would be, look over here, x is equal to f of t, so dx dt is f prime of t. If that's greater than 0, you can do the following manipulation to arrive at the integration formula for arc length when you have the arc described by a set of parametric equations. So we begin here with what we had in section 7.4, and the first substitution that we make is for dy dx. How do you find dy dx when you have a set of parametric equations? Yesterday we learned the parametric form of the derivative. If a smooth curve C is given by the equations x is equal to f of t and y is equal to g of t, then the slope of the curve at the point xy is given by dy dx, which is dy dt divided by dx dt. So we make our first substitution using theorem 10.7 from yesterday. So now we will do integration by substitution. Let x be equal to some function of t. Then dx will be equal to f prime of t dt. Another way you can write f prime of t is as follows. It is the derivative of x with respect to t. So now we can change variables. We can replace the dx with dx dt dt. And furthermore, as we saw earlier with the two curves that I sketched, f of a corresponds to one endpoint of the curve, corresponding to x naught when we had the curve described by our rectangular equation, and f of b corresponds to the other endpoint of the curve, corresponding to x sub 1 when we had our curve described by a rectangular equation. So when we change variables from integration with respect to x to integration with respect to t, our limits of integration will change as noted. So we will have f of a is equal to x naught, because our substitution is x is equal to f of t, and we will have f of b is equal to x sub 1. So for the parameter t, when we integrate with respect to t, the corresponding values of t for x naught and x sub 1 are a and b. So how do we go from this line to the next line? We do some algebraic manipulation within the radicand to go from the first line to the second line. What you can do here is you can write 1 in this form. You can write it as dx dt squared over dx dt squared. Now you have a sum. You have a sum of two fractions with a common denominator of dx dt squared. So over here you can distribute the square and have it be like this. And when you add the two numerators, you get dx dt squared plus dy dt squared in the numerator, and you have the common denominator of dx dt squared in the denominator. So that is how we go from the first line to the second line for the radicand. So now that we have that, you can apply a property of radical, a property of nth roots. If you have the nth root of a over b, you can write that as the nth root of a over the nth root of b. So using that, you're going to write what we have here as the nth root of the numerator over the nth root of the denominator. And of course, when you have the square root of a quantity that is squared, they will undo each other, and you will just be left with dx dt in the denominator. And what happens with that dx dt as we go from this line to the next? That dx dt will cancel with the dx dt there to just leave you with dt. And in the for the integrand, you will just be left with the numerator that you have there. And this is, in fact, our integration formula to find arc length when you have an arc described by a set of parametric equations. What you can do is you can either write it in this form here, or you can write it in this form here. They are the same because this is saying dx dt squared. Now x is equal to f of t, so dx dt is the same as f prime of t. So you can also write f prime of t squared. This is saying dy dt squared. Y is equal to g of t, so dy dt is g prime of t, so you can also write g prime of t squared. So we've seen how we get theorem 10.8 from the definition of arc length that we had in section 7.4. Now we look at number 47. Find the arc length of the curve on the given interval. So we see that we have our curve described by a set of parametric equations on the interval of t values from 0 to 2. So we're going to use theorem 10.8, arc length in parametric form, and the definite integral that we need to find the arc length would be from 0 to 2, and you're going to have the square root of, you need to find dx dt, so dx dt would be 2t. You need to find dy dt. Dy dt would be 2. And then you have to square dx dt. Dx dt squared would be 2t squared, which would be 4t squared. And then you have to square dy dt. Dy dt squared would be 2 squared, which would be 4. So now you're going to write dx dt squared, which is going to be 4t squared, plus dy dt squared, which is 4. And you're integrating with respect to t. So here in the integrand, you can factor out a 4. And here you have this. You can use a property of nth roots to write the square root of 4 times the square root of t squared plus 1. The square root of 4 is 2, which is a constant. And there are some integration techniques that we haven't learned yet. And this can be solved by one of those integration techniques that we haven't learned yet. But at least you get to see how to apply Theorem 10.8 to set up this problem. And there are a number of problems where you will get an integrand that you know how to work with from the integration techniques that we've learned so far. But sometimes you may get an integrand that you don't know how to work with because we haven't learned that integration technique yet. We will in a few weeks. But that's number 47, and that's about as far as we can go based on what we've learned. So we've done objective 1. We understand the proof of Theorem 10.8, arc length in parametric form. And we were able to set up a problem to find arc length of a curve given by a set of parametric equations. This half of the lesson that we're starting now has two problems similar to some of the problems from your homework for tonight. Numbers 38 and 28, and that would be the two problems that we look at to conclude our lesson for today. Number 38, determine the t intervals on which the curve is concave downward or concave upward, and we have a set of parametric equations describing our curve. Yesterday we reviewed concavity, and there is a test for concavity. If the second derivative is positive on an interval, then the graph of the function is concave upward on that interval. If the second derivative is negative on an interval, then the graph of the function is concave downward on that interval. So we have to analyze the sign of the second derivative. So we have to look at the second derivative for the curve represented by this set of parametric equations. So we begin by using the parametric form of the derivative that we learned yesterday to find dy dx, or the first derivative for the curve represented by our set of parametric equations. We need to find dy dt and divide by dx dt. Once we have dy dx, to find the second derivative, we would take the derivative with respect to t of dy dx and divide that by dx dt. So dy dx is equal to dy dt, and if you look at our parametric equation for y, we have t squared plus t cubed. So dy dt would be 2t plus 3t squared. And then we divide that by dx dt. The parametric equation for x is 2 plus t squared. So dx dt would be the derivative of the constant 2 is 0 plus the derivative of t squared is 2t. Now to find the second derivative, this is what we will use. But before you do that, you want to simplify what you have as much as possible so that the mechanics of the differentiation will be easier to do. So you have 2t over 2t plus 3t squared over 2t. So you can rewrite the first derivative like this as a sum of two fractions. So you have dy dx is equal to 2t over 2t is 1, plus I have 3 over 2, and t squared over t is t. So now I can find the second derivative by using what we have here. So to find the second derivative, I will do what I need to do. So in the numerator, I will find the derivative with respect to t of dy dx, which is 1 plus 3 over 2t. And in the denominator, I have dx dt, and dx dt is 2t. So the second derivative is equal to what we have in the numerator is the derivative with respect to t of 1 plus 3 over 2t. So that's going to be the derivative of the constant 1 is 0. So 0 plus the derivative of 3 over 2t, which is 3 over 2. And in the denominator, we have 2t. So if you have 3 over 2 divided by 2t, which is the same as multiplying by the reciprocal of 2t, which is 1 over 2t, and that gives you 3 over 4t. So now how do we use that? That's our second derivative. That's our second derivative. The question is asking, determine the t intervals on which the curve is concave downward or concave upward. So we go back to the test for concavity. The t intervals on which the curve will be concave downward are those values of t for which the second derivative will be negative. And the t intervals where the curve will be concave upward are those values of t for which the second derivative will be positive. So you need to look at the second derivative, and you will see that when t is equal to 0, the second derivative would be undefined. So you can draw a number line, and you can have t is equal to 0, and before t is equal to 0, you have t going from negative infinity to 0, and after t is equal to 0, you have t going from 0 to infinity. So on each of those two intervals for t, you can check for the sign of the second derivative by choosing a representative t value. So in other words, just choose some value for t, like t is equal to negative 1. If t is negative 1, the denominator of the second derivative will be negative, while the numerator is positive. So the second derivative will be negative on this interval of t. Choose a value for t, like t is equal to positive 1, and if t is positive 1, both the numerator and the denominator of the second derivative will be positive, so the second derivative will be positive on this interval of t. The last thing that you should do is to state your conclusion in response to the question. Determine the t intervals on which the curve is concave downward. So we write the curve is concave downward on the interval from negative infinity to 0 for t, and the curve is concave upward on the interval from 0 to infinity for t. Our last problem for today is number 28. Find all points, if any, of horizontal and vertical tangency to the curve. So before we discuss this, we would like to discuss what is meant by points of horizontal and vertical tangency to the curve. Suppose you have a set of parametric equations that gives you a circle of radius r centered at the origin. This circle has 2 points of horizontal tangency. They are going to be points A and points B. The tangent lines to the circle at these 2 points are horizontal, and the curve has 2 points of vertical tangency, and they're going to be points C and D. The tangent lines to the curve at these 2 points are vertical. So the question is, how can you find, if you're not looking at a graph, all points, if any, of horizontal and vertical tangency to the curve? To understand how to do that, first you need to understand that the slope of a horizontal tangent line is 0. And of course, what gives you slope of a line? The derivative of the function with respect to x at that particular point will tell you the slope of the curve at that point. So when the derivative is equal to 0, the tangent line will be horizontal. When do you have a vertical tangent line? The slope of a vertical line is undefined. So you will have a vertical tangent line when the slope is undefined. And of course, the slope is given by dy dx. And since we have a set of parametric equations to find dy dx, we use theorem 10.7, parametric form of the derivative, which is dy dt over dx dt. So to find points of horizontal tangency, you need to figure out the points at which the tangent lines are horizontal. In other words, you have to figure out the values of t that would make dy dx equal to 0. And then for those values of t, you will find the coordinates xy of the points corresponding to those values of t. To find points of vertical tangency to the curve, you have to find the values of t that would make dy dx undefined. And then once you find those values of t, you would need to find the corresponding x and y coordinates for those t values that make the slope undefined. Again, obviously we have a different curve than the circle that we're looking at, but I wanted to demonstrate the concept. So now you find dy dt for number 28. That's easy to do. It is going to be 2t plus 3, and you find dx dt for number 28. That is also easy to do. It's just going to be 1. So what are the t values that would make the numerator equal to 0? And if the numerator is equal to 0, the fraction will be equal to 0 as long as the denominator is not equal to 0. And of course, in this particular case, the denominator is always 1. So for what value of t will dy dx be equal to 0? We can set dy dt equal to 0, and we get 2t is equal to negative 3, so t is equal to negative 3 over 2. So that's the value of t at which the curve represented by this set of parametric equations will have a horizontal tangent line. Will there be any points at which the curve has a vertical tangent line? For that to happen, dy dx, or slope, has to be undefined, and that would happen whenever dx dt is equal to 0, but dy dt is not equal to 0 at that same value of t. That doesn't happen for our problem because dx dt is always a constant 1. So this curve does not have any points of vertical tangency, but it does have a point of horizontal tangency at t is equal to negative 3 over 2. But when you look at the instructions, it's stating find all points, if any, of horizontal and vertical tangency to the curve. I have found the t value at which the curve will have a horizontal tangent line, but what are the coordinates of the point on the curve corresponding to t is equal to negative 3 over 2? I need to substitute this value of t into my set of parametric equations to find the coordinates of that point at which the graph will have a horizontal tangent line to complete the problem. Again, I'd like to say that the circle is to help you understand the concept, and of course we don't have a circle for number 28. So to complete the problem, you need to evaluate your two parametric equations at the value of t that you found, setting dy dt equal to 0. And so when you do that, you get the x-coordinate of the point at which the curve will have a horizontal tangent line is negative 1/2, and the y-coordinate is negative 9 over 4. To complete the problem, you would state the conclusion in response to the question that the curve has a point of horizontal tangency at negative 1/2, negative 9 over 4. In the first part of today's lesson, we looked at objectives 1 and 2, where we understood the proof of the arc length formula for a set of parametric equations describing a curve. And then we used that to write a definite integral for a particular problem. And then the second part of the lesson, we did 2 other problems not related to these 2 objectives.